Welcome to our discussion on functions and models. Let's begin with looking at the four different ways we can represent a function. They are verbally, numerically, visually, and algebraically. Now often verbally just means in words, and we normally don't discuss functions verbally so much, so it's really in written words. Numerically means we're going to use a table. We're just going to list a bunch of ordered pairs. Visually, also called graphically, means we're going to graph it. And then algebraically is the one that you're most familiar with, where we actually list out the function in terms of y equals x. So here's an example of verbally. We're just going to describe the cost of mailing a large envelope in the post office, that it's dependent on the weight. Numerically, we're going to go ahead and list those numbers in the table. So there's our input and output, our ordered pairs. Right, this one here is right here. You can think of this as the x and this is the y, right? Input, output. Visually or graphically, here's a graph that shows the vertical acceleration a of the ground as a function of t time. Algebraically, we've got a simple function that describes the area of a circle based on the measure of its radius. So instead of just saying area is equal to pi r squared, we can now write it as a function. A function of area is equal to pi times the radius squared. And then of course we can put all four of them together and see that we can talk about the area of a circle as a function of its radius in all four ways. We can describe it verbally, or with the written word. We can put the numbers in a table. We can graph it. And we can list its explicit algebraic equation. Now you might be thinking, wait a minute, this isn't a circle. Remember, we're not graphing the circle. We're graphing the function of the area of a circle. If a circle has radius of 0, its area is 0, and that gives us this point here. But if a circle has radius of 1, then its area is going to be pi times 1 squared, or just pi, and there's 3.14, which is going to be right about there. Now of course all of these numbers really don't work in the real world. You can't have a negative radius, so this part of the graph really doesn't make sense, and we would most likely use this function, but we would restrict the domain. We would say the domain is going to be 0 to infinity, because it only makes sense to let the radius be 0 and positive, and then we would no longer have this part of the table, we would no longer have this half of the graph, but we'd still have the same algebraic description, and we would still have the same written description. Okay, so a function, as we've seen, is just some rule that assigns outputs to inputs, right? You give it an x, it gives it a y. We talk about f of x as being f of x, right? This writing here is f of x in English. That's how we say it. It's the value of this function f at some point x. The domain are all the things we're allowed to plug into it, and then the range is everything we get out of it. The domain is normally called the independent variable, and the range is called the dependent variable, because the height of the function depends on what value you give it. Here's another way of looking at a function as kind of a picture. You have input and output. I also like this, the arrow diagram or the bubble diagram, where you can see how each number is getting mapped to some answer, right? So you give it an x, it maps it over to f of x. You give it an a, it maps it over to f of a. The bubble on the left would represent your domain, and the bubble on the right would represent the range. The most common way of visualizing a function is to actually just graph it. And the graph is just going to be the collection of all of its ordered pairs, those numbers that we saw on the table before, but instead of just a discrete number of them, we're going to get a continuous number of them. We're going to connect all those dots, and we're going to get a smooth curve like this, or sometimes a straight line, or a combination of the two, depending on the function we have. The height of the function at any particular point represents the output for that input. So here, this height, if you take it across to that point, that is f of 2, right? That vertical distance is f of 2. The domain is going to be all of the things that we're allowed to plug into the function. So when we graph it, it's going to be the entire distance left and right that ends up having a graph. And then the range are all of the outputs, and remember the height of the function represents the outputs. So the range is going to be the total distance from lowest to highest point on the graph. With that in mind, go ahead and pause the video and see if you can answer A and B. Okay, were you able to figure it out? Very simply, f of 1 means if you plug in x equals 1, the function gives you that value there, which is a height of 3. If you plug in x equals 5, 2, 3, 4, 5, you're here, you get this as an output, and it looks like it's about negative 0.7-ish. Okay, what's the domain? Well, the domain are all of our inputs left and right. It looks like this function is going left and right from 0 all the way out here to 7. So the domain is going to be everything from 0 to 7. Why are we using a square bracket instead of a round bracket? Well, if we were going to do a round bracket, right, our domain would be 0 to 7 with round brackets if there were open dots at the end. But since there aren't, we use closed brackets. Same for the range. The range actually attains this value of 4 and this value of negative 2. So it's going to go from negative 2 to 4 with closed brackets. Here it is written up all nice and pretty, so you can read it better than my scribbling. Okay, some other representations of functions. If we're looking at the graph of something and we're trying to determine if it's a function, we have a very simple, easy test, the vertical line test. If you can draw a vertical line anywhere on the graph and it touches the graph in more than one place, it is not a function. So obviously the one on the left is, but the one on the right is not. This one obviously is not. It fails miserably, right? We can draw vertical lines all over the place, and that is not going to be a function. However, we can restrict it and get two separate pieces, each of which are a function. If you take the original equation here and solve it for y, so now you isolate y, and then go ahead taking the square root of both sides, you get y equals plus and minus the square root of this. Because remember, when you take a square root, you always got to worry about plus and minus. Well, all you have to do is take each half. The positive half gives you the upper part of the parabola. The lower half, the negative part, gives you the lower half. And now we have two actual functions that pass the vertical line test. Well, we also could have taken that original function, and instead of having, thinking about it as x being the input and y being the output, we can now let y be the input and x be the output. So now, instead of this being a function in terms of x, we can think of it as a function in terms of y, right? It's h of y. Y is now the independent variable and x is the dependent variable, and all that happens when we do that is the orientation changes. We now have that as our function. And the input is the y-axis and the output is the x-axis, and we now have a normal parabola that satisfies the vertical line test, and we now have a function. So just remember that functions don't always have to be in terms of x. They can be in terms of any letter that you want. We'll see a lot of examples of functions where you'll have something in terms of t for time, because we want to know how something changes over time, like profits, volumes of things, that type of stuff. You can have a function in terms of any variable. And it doesn't always have to be f. It can be g of, p, the g function in terms of p. Okay, how about piecewise defined functions, a special family of functions? These are functions that are just defined in pieces, ergo piecewise defined. You'll normally see the description of them in something similar to this, where you've got two pieces or more, right? In this case, we only have two pieces, but you could have more if you wanted to. So we've got a red piece and a blue piece. Well, what you need to do is recognize where is the cutoff, where is the delineation, right? If we were to look at our normal xy axes, right, our Cartesian plane, where's this cut? It's cut at x being less than or equal to -1 or greater than -1. So if you go over here to -1, you're basically cutting the Cartesian plane into two pieces. You'll have a left side and a right side. The left side, we'll call it side A, is the A stuff, right? Because that's where x is less than or equal to -1. And then the right side, we can call that side B. That's the blue stuff because that's where x is defined to be greater than -1. So all that we're doing really is we're graphing two separate functions on the same set of axes, overlapping them, right, but only allowing them to live on their side of the line. So this function here, x squared, that's easy. We know what that is. That's a parabola. And then this side would be something like that. But it doesn't live on the left-hand side of the line. So we can't have that whole thing. Instead, we can only have to this point here, stops the line, and in fact, because it's a strictly less than, it would have an open circle. Then we look at the other function, and this is simply y equals 1 minus x. If you want to write it as -x plus 1, you can now see that it's a straight line with a -1 slope and a y-intercept of 1. So it hits up here at 1, and then it has a negative slope, right, which means it's rising as we go to the left, falling as we go to the right, and it, dot, 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 doesn't really exist over here. Then it gets to here and it keeps going, and this one has a solid dot because it's a less than or equal to. And that's it. It's that simple. Here it is with a cleaner picture for you, and you can see that you just have two pieces separated at the -1 part. Another piecewise defined function that you guys are very familiar with is the absolute value function, because the absolute value function does two things. If you give it a positive number, it gives you that same number back, and you basically get y equals x. However, if you give it a negative number, it gives you a positive number back, which is the opposite of the number you gave it, and you get y equals -x, as we see here. We get x when it's a positive, -x when it's a negative. So we now have something, a function that is separated, right, in two different pieces at x equals 0. So the y-axis ends up being kind of our line of demarcation, right? Something to this side, something to that side. Over here on the right-hand side in yellow, we get the simple line y equals x, and on the left-hand side in green, we get the simple line y equals -x. Another example, if we go back to the description of figuring out how much it costs to mail an envelope, well, we have these set prices. If the weight's between 0 and 1, probably let's say ounces, it's 0.88. If it's between 1 and 2 ounces, it's $1.05, etc., etc. Then we get what's called a step function, because if you graph it, it looks like stair steps. So from 0 to 1, right, as the weight of the package goes from 0 up to 1 ounces, you're held at a constant price. And then as soon as it gets above 1 ounce, you now jump up and have a different constant price. How about symmetry? Well, if we have some of our more standard functions, we can test them for symmetry. We can graph them and see if they're symmetrical with respect to the y-axis. And symmetrical with respect to the y-axis just means if you go the same distance in both directions, right? These little stripes here mean that this distance and that distance are the same, and then the little double stripes mean that those are the same heights. So if you go the same x value in both directions, you get the exact same height. That's what we call an even function. It means that if you plug in a negative value into the function, you get the exact same answer if you plugged in the positive value. So f of 2 is going to equal f of negative 2, f of 3 is going to equal f of negative 3, and so on and so forth. An odd function does just the opposite. When you plug in a negative number into an odd function, it gives you the opposite that you would have gotten from the positive. So that means f of negative 2 is going to equal 3. That implies that f of 2 must equal negative 3. Or if you have f of 5, let's say, equals 7, then f of negative 5 must equal, you got it, negative 7, right? We'll do one more. If f of, let's say, 4 equals negative 2, then f of negative 4 has to equal, you got it, positive 2. It's that simple. The graph of an odd function is symmetric with respect to the origin. It's kind of hard to visualize. This picture I don't think helps a lot. The idea is, okay, it's not symmetric with respect to y, right? If you fold this in half left and right, it's not going to be the same. It's not symmetric with respect to x. If you fold it in half that way and fold it vertically, it's not going to be the same. What it really is it's a double fold. If you fold it over here and then fold it down there, you get the exact same. Do you see how that works? If you fold it to the left, you'd get something that looks kind of like that, right? And then can you see how these are now mirror images of each other? You know, except for my bad drawing skills. So that's what symmetric with respect to the origin means. It's kind of like a double fold. Okay, if you want to determine if things are odd or even, you can graph them and look at the graph, or much easier is to just check and see if they hold with their properties. We know that if something is even, f of negative x has to equal f of x. Now you can't just check this for a couple numbers. It's not like you can plug in 2 and negative 2 and make sure they're the same, and then 4 and negative 4 and make sure they're the same. That's not good. You have to do it algebraically. So what you need to do is just plug in negative x, right, into the function. And if you plug negative x into the function, you end up getting negative x to the 5th, which is just negative x to the 5th, right, because negative times negative, you do that 5 times. You still get a negative number, plus negative x. You can factor the negative 1 out of both of these pieces and see that you get this final result, which is just the original function times negative 1, and you go, aha, that's an even function. Okay, how about the next one? When you plug in negative x into the next function, you get 1 minus a minus x to the 4th, but minus x to the 4th, right? When you raise a negative number to an even power, it just becomes even, so you get 1 minus, right, positive x to the 4, and that was the original function, so it's even. The last example, you plug in a negative x into the original function, and you get this. Well, the original function, if you don't remember, right here, 2x minus x squared, so the original function of 2x minus x squared, well, they're not the same, and if you take this and multiply it by a negative 1, you get negative 2x plus x squared, so it's not the same as the original function times a negative 1, so it's not even, it's not odd, it's neither. And in fact, the vast majority of functions are neither. Only special functions are even and odd. Here's the graph. You can see the first one was odd because it's symmetric with respect to the origin. Second one was symmetric with respect to the y-axis, right? It's left and right symmetry, so we know it's even. And the third one is not symmetrical with respect to either of them. It's actually, you know, if you care, it's symmetrical with respect to the line x equals 1. Right? It's symmetrical around that. But that's not what even is, right? Even is symmetrical with respect to the origin. Okay, last but not least, increasing and decreasing. You guys all know what increasing and decreasing means. It means going up and going down. So if you're looking at a function, very simply, we can see where it's increasing and where it's decreasing by where the function is going up or going down. Now when we talk about where it's increasing and decreasing, we talk about it in terms of x. So that's why we say that the function is decreasing, right, on the interval b to c, because it's all about the x intervals, not these capitals, these lowercase ones. And then we say that it's increasing on a to b and c to d, because we can see it's going up, right, on this interval and then going up on that interval. So it's always in terms of the x values, the inputs. This is just formalizing it that we know a function is increasing if its outputs, its values, are getting bigger as the inputs get bigger, and we know it's decreasing if the outputs are getting smaller as the inputs are getting bigger. And you go, no, duh, that's totally what it's intuitive. The last example that we'll look at is our friend the parabola, which we're going to see a lot of, and we can see that this function is decreasing everywhere on the negative side, right? So as we go from negative infinity to 0 with our x values, the function is getting smaller, and then from 0 to infinity it's getting bigger. So it's decreasing on negative infinity to 0 and increasing on the 0 to infinity interval. And that's everything you need to know about the 4 different ways of representing functions.